the first thing we do as architects before we get into the cost is we might have some discussions with the contractor if there was a contractor on board. But the number one thing is the use of the building. I can't write. Can you stop sharing for a sec?
Sure.
Okay. Okay, so can you see when I write here, can you see it?
Yes.
Okay. So the first thing is the use of the building. And what does that mean? The use and the occupancy of the building. If you have a building that you're expecting to have a heavy load in it, for example, like a library, it's going to be different than if you're designing a house. A house, you can just build it out of wood, right? Because the amount of things that are creating the load in the building are not very heavy. But if you're designing a library with a lot of books in it, those books can be really super heavy, right? And that's just a kind of a high level example of how use can dictate the loading. And if you talk about loads, have you taken structural courses at school?
Yes, I had taken before.
Okay. And do you know the type of loads that you would calculate or you would look at or analyze in a building?
Concentrated and unconcentrated.
Those are the way the load is applied to structural members. And usually we have live loads.
Oh, okay. Yeah, live load.
Loads. And and some other like wind loads and other things. But from the inside, usually live and dead load are pretty important. And so a lot of the sizing of the members that they used in their report are going to be based on the loads that they're generating. So use has a very important influence on the building. The other one is something called construction type, which I'm not going to get into it too much because I don't know if you've taken stuff like that before. Construction type is very, very important. A lot of times the building code will not let you design a building that's very, very, I would say, tall or big or large, has a big footprint, or very tall, without going to a more robust structural system. So sometimes, and the construction types range from 1 to 5. So you have 1, 2, 3, 4, and 5. 1 and 2 dictate that the structure is going to be either concrete or steel. 3 is usually timber, heavy timber construction. Do you know what that means? Do you remember that from structures? Heavy timber construction means that the members, it's engineered wood, like member sizes that are more than 6 by 12, plus or minus. And there's a unique property to these. It's glue lam, for example. You've heard of that term? Glue lam? Have you heard of that?
No.
So these members are called engineered wood members. And they can also be natural timbers. They're cut out of the trees and they're really large. And they have a unique way of burning, and we're not going to get into that too much. 4 and 5 usually, actually I'm going to take that back. I'm sorry, here, I'm going to correct myself here. Okay. 3 and 5 are usually wood framing, and then 4 is the heavy timber. Okay? So construction type, so if you're asking, like, how do I figure out what type of structure do I need for this building? First of all, you're going to start with the building code and what the building code allows for the size and height of that building. And then 2, you're gonna look at costs. Now, for a project, I don't know. So you haven't selected the project, so I really don't know what to recommend. But usually, if it's an office building, hospital, usually if it's an institutional building, in most cases the structure is going to be wood or steel. You're not gonna, concrete or steel. You're not gonna do wood unless it's maybe residential scale, like an apartment building or houses and so forth. Okay, so that's number one. Now the number two is we do the other more important thing is we actually start with the foundation system for the building. I don't know if your structural analysis in your report. Let me look at that for a second. Let me open it. Do you know what page the structural analysis starts?
No, sir.
Okay, so structural design. After determining the layout, we sort of developed schematic for the structural plan, location of beams, columns. Okay. Structural plans, I don't know if they go into foundation systems. No, they don't really get into foundation systems too much. Okay, but if you're going to do it right, that's how I would recommend it, is you do an analysis of the type of foundations to do it, and obviously in a hypothetical project where you don't have a lot of information on the site, you're going to start to make some recommendations. For example, if you're designing a tall, 20-story building, you're not going to put a shallow foundation under it. You're gonna probably go to a deep foundation. And do you remember foundations from school? From like structures, do you remember the different types of foundations or the different options?
Do you mean footings?
Like footings, that's right. You have single footings, continuous footings. You have pile foundations where you dig deep down into the earth. Anytime you're extending down into the earth, that's the deep foundation. So another part of this is determining the type of foundation system you're going to use. And then you move on to the superstructure. Okay, so the first thing that you would do if you're trying to, I'm going to erase this.
Like, do we usually absorb the floor plan, and from the floor plan we can do the structural analysis? Or?
Yes. Oh, absolutely. So let's say you have a building that, I don't know, shaped like this somehow, something like that. I mean, you've designed the building. Maybe there's a lobby here. Maybe there's some offices here. Let's say this is some sort of classroom building. This is your building core, your elevators and stairs are here. This is another like admin office area down here. And then you might lead into a corridor that exits out. There's another stair. I'm just making things up, okay? And then you've got large classrooms like that. So that's a classroom, that's a classroom. Let's say you have something like this is a large auditorium that you enter from the lobby. And that's your design for your building. And the first thing you got to do is certainly start to lay out a potential column grid for the building. Now, normally, dependent on the structure that you select, there's rules of thumb that you would follow for the grid, for the structural grid, right? And when I say structural grid, and usually if it's a steel building, you've got columns, you've got beams, and then you've got a floor system, right? The floor system is usually a composite, what they call a composite system, meaning it's made out of concrete and steel at the same time. With concrete, everything is concrete, right? You've got a column beam condition, and you have some sort of slab system. If it's a one-way slab, you're probably going to see the beams. If it's a two-way slab, that means it's a self-supporting slab with the beams embedded in it. So you don't see any beams, you just see columns and slab, that's it. But in a two-way slab, the slab is thicker. So forth. So there's some rules of thumb that you follow with these types of things. For steel, if you're thinking about steel, steel has spans up to 40 feet. You can do spans up to 40 feet. For that type of span, your beam depth is about 2 feet deep, minimum. Okay? For concrete, you can get up to 30 feet with a 2 foot deep beam system. So, with steel, you're getting longer spans. That's also another influence. Like, so if you're looking to design a space and you don't want a lot of columns, well, you go to steel because steel can span more. Now, you could do post-tension concrete or pre-tension concrete, and you could do 60 feet with concrete if you wanted to, right? But that's a more expensive system. They do that in parking garages a lot. I'm sure you've seen them. Like, there are precast concrete beams instead of cast in place. If there's anything that you don't understand, if I'm not making sense to you, let me know. I could re-explain it, okay? Please stop me. I want to make sure that you're benefiting from your time with me. So you start with a grid. I want to pick somewhere where you don't start like, I'm going to start from this corner or go this way. You don't start like that when you start to draw a grid. Okay? I start at the most important places. I start like somewhere here. Like, I know, like these, I don't want columns here, so maybe that's one grid, column grid here. That's another one, and that's another one. And I could do this, that's one column grid, and this one. So now I've laid out a hypothetical column grid in this direction. This, I'm assuming, is not going to be more than 30 feet. Let's say this is concrete. And that's how I would lay it out. And then this, you start from this direction, you start laying it out that way. Maybe you just find places where the building starts to shift and break. You want columns to help with that break. And there's going to be a column here, a column here. Now, there's a column here, so maybe I would want to shift the wall up a little bit and put a column here. And maybe now this stair that I drew earlier, maybe it wants to fit a different way to align with the column grid. Because it's not just a one-way where the architecture determines everything. Sometimes the structure is going to start to dictate certain things. Do you see how it's starting to develop?
Yes.
So the round things are potential structural location for a grid. And now I could lay out, put grids, and then determine the orientation of my slab or my trusses. If I'm doing steel, if I'm doing concrete, it's all going to determine what the orientation is. Now, without doing more analysis, you're not going to know what type of additional things you're going to need. Like, unless you're a structural engineer. We're not structural engineers, we're architects. So we know a little bit of structure, enough to be able to lay out a grid, enough to use some rules of thumb, maybe solve some structural stuff, but it's up to the structural engineer who's to determine all these things, right? Why don't you share your screen again? Let's go through each segment in that analysis book, and let's make sure that you understand each of these parts and figure out what else do you. So now you have an idea. I mean, if you have a project, do you have a project that you designed in the studio that we can lay out a structural grid for? I just want you to practice. Because part of it is really, again, how do I use these rules of thumb to lay out a grid for the project? But before we do that, let's go back to the report since we have time allocated for doing this. Let's go back to the report and see if you don't mind sharing your screen one more time. Or I can share my screen if you want.
Oh, okay. That's better.
All right. Okay, so do you see my screen?
Yes.
Okay, so here, after determining the layout of both structures, and the structural plan, laying out the columns, beams, girders. Do you know what a girder is?
Oh, I'm not quite sure.
Okay, so beams are, it could be anything, right? Anything that spans between two columns, any member. You know, if you have a column here and a column here, and you put a piece of metal or concrete or steel and connect it here and here, you know, if this is the ground, if that's a column, that's called a beam. Now sometimes when we have a very complex structure, you know, we might have beams going this way. Let's say this is like 60 feet, right? You might have main beams going this way, but you might have secondary beams going this way, right?
Mm-hmm.
Have you seen that in structures before? Like you'll have a column here, column here, column here.
Do you mean the slabs?
No, I'm just drawing a roof plan for just a generic building. I want to just explain to you that sometimes you might have these main beams, and sometimes you might have secondary beams that are sitting and filling the space, because you want to be able to fill a space for you to pour a concrete slab. Well, here in the US, they call these big beams girders, and then the small beams are still called beams. Okay?
Okay.
So what he did here, he located the beams, the girders, and the columns. So this is really what he's talking about. So he did, starting with the classroom building foundation of 1 foot, starting with the classroom building, a foundation of 1 foot, 4,500 PSI rated concrete will be poured. Okay, so what he's saying here, they decided that you don't need a heavy foundation. Now this is actually not correct. You would never do that in real life. You would never put a foundation that close to the slab, because you want to push the foundation down into the ground at least 3 feet below the slab. And the reason to do that is to prevent uplift and prevent like water coming in underneath it and freezing and raising the building. But he decided that instead, you know, all these columns, I'm going to put them on a large footing. And this footing is going to be 1 foot deep, and it's going to be made out of concrete that has a bearing capacity of 4,500 PSI. Do you know what that means? Yeah, do you know what that means?
Pound square inch. I know PSI is pound square inch.
Pounds per square inch. So, but that's the bearing capacity of the concrete. So that concrete type, that concrete mix, when they poured it in, can withstand 4,500 pounds for every square inch. Okay? So dependent on the size of this footing, if this size of this footing, let's say, is 4 feet by 4 feet, right? That's the size of the footing. The area of the footing then is 16 square feet. Right? And 16 square feet times 12, 12 square, right? Gives you, I'm just going to change it to square inch so that we use the same units. 16 times 12 times 12. That's 2,300 roughly square inches. Now, times 4,500 psi, that means that that footing can carry 10 million pounds of weight. Does that make sense?
Okay.
So it's just some quick math. You can figure out how big that foundation needs to be, or if the foundation is adequate. Now there's the depth that's also involved in that. So the deeper the foundation, it's not just the area. Now the area helps distribute the load, right? The bigger it is, that helps distribute the load evenly into the soil. Now I don't know where he got that from. Normal weight concrete is about 3,000. Well, that's probably not normal weight. That's probably normal weight concrete, actually, not lightweight concrete. Lightweight concrete is used maybe for interior slabs where it's not load bearing. 4,500 is normal weight concrete. So that's just a rule of thumb that he's using for the concrete. Now for the structure, they said we decided to go with a W6 by 25 column, a W12 by 14 beams, and W10 by W8 by 10 for beams, and LS 5, that's another L-shaped framing member bracing for the support. The roof structure is a monotruss system was constructed using a pre-downloaded family and visual analysis. Okay, interesting. This is not a very well written report in my opinion. I'm going to delete all this stuff. All right. Okay. Main structure. So due to the visual analysis, the limitations when designing the main building, the building needs to be divided into separate sections, the center and sides, single foundation. Okay. Let me just skim through this just to see kind of some additional points that they were trying to make it. Okay. The loads. Now, do you have the ability to do structural analysis diagrams like these? Did they teach that to you in class? Be able to extract these shear and moment diagrams?
Yes, the shear moment I know, but
what did they use to create those? Because those look like they used this project, Visual Analysis 19. That's the software they use to create these diagrams, right?
Okay.
Do you have access to that software?
Oh, I will soon.
Okay. I don't have any knowledge of that software. Never used it, never heard about it. But it looks like it's a place where you can input loading information and it'll generate analysis diagrams for you and tables for you and make sure that you pass the structural requirements for each of these load variations. Okay, so if I was going to do this, obviously we need to get the hands on that software, right? We need to get our hands on the software, be able to understand how to use it. Two, we have to really understand loads, because if you don't have the proper loads, you're not going to be able to figure out anything here. All of these reports are from that software.
Okay.
It's just, it goes and analyzes every single member of the trusses. And this is getting into mechanical design. So, yeah. So let me go back here and just go to the loads. The load table is super important. That's where I would start. This is where I would start. You would figure out how much load you have on the roof between dead load, live load. If it depends on the area that you're in, you might have snow loads, right? If this is in the northeast United States, then where are you right now? You're in Texas?
Yes, Kingswood.
It doesn't snow in Texas, right?
No.
So that's why they don't include snow load. Here in the mid-Atlantic, obviously it snows in the winter, so we have to do that. You do wind analysis, and there's different types of winds, so dependent on the orientation and the main direction of the winds, where the winds come from, you have to find out what that information is for your specific territory. Sometimes it's coming from the west, so the west becomes the windward side, and the leeward side is on the other side. And then the side walls are these ones here, and then the roof wind load. So this is really important. So if you look at a building, and if wind is coming to it, it'll go up and over and around. And then here, it'll create negative pressure that pulls load up, that actually pulls the building up. On this side, you get similar negative pressure here. And then here, you're obviously pulling right at the building. The wind is just hitting it. The sides also behave differently. These dimensions, these factors, you actually will get them from the AEIS manual for structures, which should be given to you. If this is part of your class, they should have given you access to it. And if not, I think I have some resources in my office. I'm going to try to bring them, and then you can find that information there. The floor loads depends. If you're a single main building center, I don't understand. This is a classroom. There's multiple buildings here, and then they just redo the calculations. But in addition, one thing that they did not do here is like loads on the floor itself, because they didn't design that floor. So dependent on your building, if it's a multiple level building or is it a single level, you might need to calculate occupant loads. So like an office, if it's an office building, it's 100 pounds per square, 100 pounds per square foot or square inch, I forgot. Maybe PSI. If it's a live load for occupants, the difference here, dead load and live load. But the way to do it, lay out the structural grid, right? These you might have to make some assumptions on, but they should be based on the loads. And you would analyze worst case scenario for the columns, and maybe you would just use that column everywhere. Do you remember from your structures class, do you remember how to calculate, or like let's say you want to get the load on this column. Do you remember how to do that from your structures class? Like if you had this as a bay, you had loads of, let's say, 100 pounds per square inch on this slab, right? But this slab distributes that load to 4 columns. Each one of these columns will get 25, right? Because the load will go in 4 directions. Do you remember that?
The load goes in 4 directions because of the shear, right?
No, it's just anything. So you put you're carrying this. You're carrying. Let's say this is my phone. I'm carrying it on one finger. Let's say I'm going to try to balance it on one finger. Right? So right now, all of this weight for this phone is going to one finger. If there's one column, all of that weight is going to that finger. If I put 3 fingers, now this weight is being distributed on 3 fingers, right?
Yes.
It's the same idea here. If you have a slab and you have 4 columns in the corner, the weight of that slab is going to get distributed on the four corners. So each column will get a quarter of the weight. It starts to get complicated if you have something like this, where you have a multi-bay situation, because this column now is getting a quarter from here, a quarter from here, a quarter from here, a quarter from here. So this column in the middle gets the most load, while the columns on the exterior get the least amount of load. Do you want me to redo this one more time for you? And do you know why we're doing this? Do you know why we're having that discussion about it? It's
load solution too.
Here, let me just do that one more time. Okay. Bear with me for a second while I erase it. So let's go through the steps one more time. What is step one? If you're given you have a task to analyze the building structurally. First of all, you understand the use. You determine which system you want to use, whether it's concrete or steel. Right? If you're concrete or steel, you have certain assumptions for the grid size. So you lay out the grid for the columns based on that size. Right? Step number 3 is you determine all the applicable loads on this building. So roof loads, live load and dead load, wind loads, and any other loads that you want to add to this building based on your the given. Here it is. They just had wind load and roof load. Exterior wall loads is just, I don't know what that is. I think it's the weight of the exterior wall. So they didn't have anything else. Usually there's occupant loads, there's snow loads, there's other things. You might be designing against an earthquake. That's a whole other thing. Okay? So step number 1, we determine what structure we want to use. Step number 2, we lay out a conceptual grid for the column based on assumptions for span. Step number 3, we determine all the applicable loads on the building and we calculate them. Okay? We find out what the wind loads are and so forth. Then we look at the roof plan, we determine what that load is, and if you look at this, and I think once you get your hands on the software, it's going to help you. This table here also includes, in addition to that, load combination equations, which I'm not sure how the software uses those. But I'm not going to get into it because it seems so complicated at this point. But this software, apparently, you can input in all these loads and it'll do an analysis of the framing for you to make sure that the sizes you're assuming are correct. Now, when do you think you'll have access to that software?
Soon. Maybe
okay.
1 week, 2 weeks.
Okay, and when is this assignment due?
No, it's actually, I'm preparing for the final project. It's gonna be like after 3-4 months.
Oh, so you have some time.
Yes.
Okay. So maybe one of the things you could do is maybe do a little bit of research on loads, calculating loads. How do I, assign a load to a column, from the roof, like the distribution of it. So this is what I was trying to do earlier. Let's say you have this building, right? And you've got this grid, and you've got a column here, 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 and here. And you've determined that the weight of this slab and the loads are like, 1,000 pounds per square inch. That's how much load is on that slab. You can say, well, if I do something like this, oh, sorry, that's the wrong way to divide it. if I do something like this for all of these, this is how I'm just cutting each segment, each one of these, I'm just cutting it into 4 pieces. And I'm going to say, when I cut this slab, which is like, I would say 20 feet by 20 feet, if I cut the slab into 4 sections, this section of the slab, now which is at 100 pounds per square inch in weight, is going to be carried by this column. So that's how much that column is going to, that's the load on that column. And based on the load, you're going to calculate how big that is. So let me give you a simple example. There's calculating the design of a column based on like Euler's formula, which involves buckling and stuff like that. It's too complicated for me to explain today. But I'm going to give you a simple analysis that's going to help you. So you know that the stress in a column is the force over the cross-sectional area. Do you remember this formula from your structures class?
Yes.
So, if you're calculating stress is in pounds per square inch. And pounds is the force, and A is the area. Right? So, if I know how much, if I know the force, and I know the stress, which is this one, it's the carrying capacity of the concrete. Remember the foundation that they give us, they use 4,500 PSI concrete. The same thing, that's given, that's the property of the material. I can determine how big this column needs to be able to carry this force. And then based on that area, I can go to a table and find a beam or a column that has that area, and then that's the column that I'm going to use in the plan. Does that make sense?
Mm-hmm. Oh, yes.
So based on the stress formula, I can determine how big the column needs to be. Now, tell me how much. What is the area? It's called the tributary area. If you're looking for the right name, it's called the tributary area for the column. What's the tributary area for this column that I just highlighted? What is the tributary area for this one? For this one, it was this guy. It was this area, which was like 10 by 10. How much is it for this guy? Where is it for this guy? Can you guess? If you don't know, it's okay. I'll help you. This is not a test.
Actually, no, I'm not sure.
Okay. If this column takes the corner, this one will take the corner from that section, but it's going to also take the corner from that section. So it's going to take this corner and this corner. So this column actually carries more weight than that column. What about this one?
This one is the same as the right one.
Good job. Okay, what about this one?
This one, the 2 squares.
Two squares. Yeah. Okay, what about this one?
4.
Exactly. This one, as I mentioned earlier, this column carries the most amount of weight in the building. And then the corner columns, because it carries 4 squares, but the corner columns only carry 1 square. So they carry the least amount of weight. Okay? That's how you can size the column. You figure out the area, the tributary area, and that's going to help you determine how much of the slab or the roof it's carrying. And based on the load on the roof, you can figure out the area of the column based on the stress formula. And you should go to the table to pick it out. Does that make sense? If you'd like to get more into that, once you get to the assignment, we can get into like real problems and do it that way. Because I just don't know. I'm looking at this, your document, and I just don't know what they used. Like they just said, we're going to assume for the structure, we decided to go with this. Now, W6 column is really tiny. That's a really tiny column. I don't know why they made these decisions without doing a comprehensive structural analysis of the load, the tributary area for each load, and so forth. It seems to me that not really very well thought of. So I think it'd be good to ask, if you have your professor that's guiding you with this class, just ask him, like, what's expected of us in terms of the amount of analysis that you need for this report. Like, am I supposed to go and do the calculations to be able to determine each column size, or do I make assumptions? Now, I can make assumptions. I've done this enough that I know, like, 10 by 10 column for a 30 by 30 span would probably work, like a W flange. Just a normal weight, like W10 by 28 would work. Because I've done projects in the past that we did similar sizing for. But I think if you're trying to do this right, I would ask a few more questions about how did they make assumptions? What did they do to select the column and beam sizes? And maybe we can come back and look at this in a little bit more detail. Does that help you in any way?
Yes.
You sure?
Yes, I'm sure. I always like to watch the recording, and I will watch it again and then get benefit. Okay.
All right. Sounds good. If you'd like to just do more lessons, or if you'd like to get into something in more detail, let me know in the future. And I'd love to help you if I can. If I can't help you, I'll be honest. I'll tell you I'm not an expert at structural analysis, but if I can do it, I'll be able to help you without a problem. Just let me know, okay?
Okay.
Do you have any questions that you want to ask before we...
No, thank you, sir.
Finish the session?
No.
You sure? Okay. Okay, Yusuf, nice to meet you, and good luck, and I'll look forward to hearing from you, okay?
Okay, thank you, sir.
Oh, not a problem at all. Okay, take care. Bye-bye.